everyone. Welcome to our physics project, where we will use Bernoulli's equation to help us determine the pressure inside my pipe using the delta Y of the water and how high it shoots out of a water spout. Let me demonstrate how our project will be.
Here is how our experiment will be done. First, I will draw a hole in the 3/4 inch diameter end cap as the hole. The water will exit out of here. Then, I will assemble the 3/4 inch apparatus. This is a straight pipe that has the hole at one end and a connection to my hose at the other end. The connection is to a 3/4 inch hose. Then, I will measure the height of the hole and the height of the faucet off the wall. Subtract these values and I'll have the delta H value for the pressure, basically the one in Bernoulli's equation where that H value for the difference in the heights of where the water goes in and where the water goes out. Then, for my experiment, I will turn the faucet to quarter, half, and full rotations. I will measure the average height of the water over the course of 1 minute. This will be our trials because water is not a very set thing, and unlike my potato cannon experiment, I can't have multiple experiments of it because the one variable I set is the amount I open. I will use the 1 minute as my 3 experiments for each setting. It'll be the average height because the water will approximately be the same for the entire period that the thing is open. Okay, then I will use a reference yardstick to confirm the height. Basically what I'm doing here is I'm taking a picture and then using drawings online and scaling just to confirm the height. To find the velocity, I will use velocity is equal to square root of 2 times 9.8 times the height. To find the velocity, I will calculate the areas of the hole in the faucet. 3/8 inch for the hole and 3/4 inch for the faucet. I'll convert the speed to the faucet speed, so I get the velocity area is equal to velocity area, and then derive Bernoulli's equation to find the faucet's pressure in terms of everything else. And then I'll plug in the values, and I'll be able to find the pressure for every individual test. My general hypothesis: the pressure of the faucet will increase as it is incrementally opened. The pressure will likely not increase linearly because the opening of the faucet changes the area inside controlling the flow. I want to find the pressure at the faucet's exit, which will be held constant. That's the 3/4 inch part. The percent faucet we open, 25%, 50%, and 100% will be the independent variable. The height, velocities, and pressure will be the dependent variables. Our constants will be gravity, of course, as well as the diameter of the pipe, 3/4 inches for the pipe and 3/8 inch for the hole.
So here, the water will exit my wall through the faucet, which goes through the pipe, and then goes up the apparatus. The apparatus in testing will be completely straight, and the water will shoot out of this 3/8 inch hole at the top, where it will have a very high delta Y into the sky. I will use digital scaling by taking a picture and then scaling it in vector graphics to see exactly how high the water will shoot. The pipe will take a shallow 90-degree turn in order to reduce head friction as it makes a 90-degree turn. The experiment will be done like this. My 3 conditions will be how much I turn the faucet by. My faucet can turn a full 180 degrees. This will be the highest option. So my first test will be a quarter rotation. This should be the lowest. My second test will be at half rotation. And my final test will be a full rotation. And these will be my 3 variables. I will then average the height out for exactly how high the water shoots. Again, I'm going to correct the height to make it shoot vertically. In order to measure the height aspect of Bernoulli's equation, I must know the delta Y of the water inside the system before it was sprayed out. My faucet is 21 inches above the ground. My apparatus, after I measured it, was 49 inches off the ground. This makes a delta Y in terms of the pressure, or the H value, to be 28 inches. Again, I will convert all my values to metric meters in order to allow the calculations to be done correctly. And there we can find our height, and that will allow us to plug it into Bernoulli's equation and get the correct pressure. This is trial number 1. The faucet has been turned a quarter rotation, and this is how high the water went. Here is trial number 2. This is the height of the water when the faucet has been turned halfway. At maximum pressure with the faucet completely open, this is how high the water went. Here are the completed calculations. Using the speed as the water ejected from the hole and the areas. So we have the diameters of the hole. They're in inches. I converted them to meters. This is the radius of the hole and the faucet, and the area respective of each. Then we can use this equation, the hole's speed times the hole's area, divided by the faucet's area is equal to the faucet's speed. And this value turns out to be 0.25. So we just divide all the speeds of the water ejecting from the hole, divide by 4, and you'll get the speeds as it exits the faucet. Then, right here, we have Bernoulli's equation and the derivation that I will be using in order to do this one. So, we're finding pressure 1, which is what's the pressure coming out of the faucet. We know that atmospheric pressure as it exits, so 100,000 pascals. For the delta H, we did the difference in the height between the exit of the apparatus and the exit of the faucet from my wall, so it's 0.7112 meters. So this is 1,000 density of water times 9.8 times 0.7112. And then here we have 1.5 rho, so that's just 500. Final velocity squared, so V2 would be the exit speed minus V1, which would be our faucet speed. So here are our equations for our 3 trials. Here are the average pressures that we have in here. And this was with quarter open, half open, and full open.
As for our conclusion, the experimental values match the hypothesis exactly. Opening the faucet more increased the pressure in the system, thereby increasing the velocity, and thereby increasing the height that the water shot. The water's height also did not increase linearly as the faucet opened more. On a other note, when the values were plugged in as a regression, the values had a larger r-squared value as a natural logarithmic regression than as a linear regression. So on the left, you'll see the linear regression, which is about r-squared value is about 0.74. And on the right, you'll see the natural log regression, which has a significantly higher 0.9 r-squared value. So it shows that its pressure is increasing logarithmically.
There are a few inaccuracies about this project. The main thing is because of the cap. Because the cap has a 90-degree bend on the inside, this will cause some head friction as the water rushes out. This means that the velocity will actually be slightly lower because some of the velocity is lost to friction on the inside, meaning that in reality, the pressure inside would actually be higher because the water would spray higher should there not be that friction. However, this is the only size of the cap I could find, and there really isn't any needle-shaped caps. So I believe that hopefully this error is negligible compared to the overall pressure of the system.